All right, thank you very much. So yes, so the next 15 minutes or so, I just want to give a little motivation and overview of the type of questions that we possibly study where quantum technology meets gravity. Now, let me start the talk with this slide. So what you see here is a picture of a black hole. Now, a black hole are objects that exist in nature, this we know, and these are so extreme and unusually and bizarre objects that they change the flow of space and time around them in a way which is very hard for us to imagine. So this type of object here is an illustration, what you see, and what it does is it bends time and space in its vicinity so that when light comes from nearby stars, it is actually bent and shaped in such a way that you get this very strange ellipse around it. So that even the angle of how the light is coming from the stars towards us as observers is changed. Now the objects are called black holes because inside of these objects, the gravity of these stars that became black holes, the gravity is so strong that light cannot escape it. So it's completely dark. So there's no way that we can get any information from outside of this black hole. And that's why all we see is just the stars around it. Now, these black holes have been predicted by Einstein by his theory of general relativity. And this is the modern theory of gravity as we understand it today. And I chose this beginning because just a few days ago, the Nobel Prize of this year was awarded to people who have been studying black holes for decades. It has been studied mathematically, like Roger Penrose, showing that they can actually really exist because the theory of relativity is so complicated that we're not actually fully sure what exactly it predicts and what may possibly be occurring in nature. And then the other two recipients actually showed observationally that with near certainty, there are black holes ubiquitous in the universe, and in fact, in nearly every single galaxy at the center of it. Now, as I said, black holes are a prediction of the theory of gravity as we know it today. And this theory was formulated about 100 years ago by Einstein, and that's what we call general theory of relativity. And it understands gravity in a very unusual way, something that we couldn't have imagined before. Namely, gravity is not a force that binds particles together or attracts them to each other, but it's just the notion that all massive objects bend space and they bend time around them. And just from these very basic principles, a lot of unusual and interesting phenomena follow. So one phenomena is that I mentioned are these black holes that we now observe in the universe. Another tractable and measurable phenomena is what we call time dilation. And that is the notion that clocks tick much slower when they're closer to a massive object. So actually your feet age slower than your head. The effect is small, but it's measurable with technology and with clocks that we have today. There are other phenomena that we also all heard about, like gravitational waves. So these are ripples of changes of spatial distances and also time as it propagates through the entire universe. And gravity, as we understand from Einstein, can be applied to even the entirety of the universe itself. And this is what we study in cosmology. It's an own field of research. And we understand that what is predicted by Einstein's theory is actually an expanding universe, which we also observe from current observations in space. Now, it has also bizarre and unusual predictions that we're not sure about even still today after 100 years. One such prediction is time travel. So actually, the theory of gravity by Einstein allows for the possibility to go backwards in time or to have regions of space in the universe where going through them allows you to go back in time. And we still cannot make sense out of it. So there's a lot of mysteries that still need to be explored on this level. Now, in parallel to the development of gravity, we had a different development, and that is the development of quantum mechanics. Now, that was another revolution of our understanding in physics, also developed around 100 years ago by many people, not just Einstein, but many other people at that time. And its goal was to explain phenomena that we observed in the atomic realm. So exactly the opposite scale, not the large scale of the universe, but the smaller scale of the universe. Now, to explain these phenomena, it turns out that we had to invoke entirely new and counterintuitive principles, some that we haven't encountered before and we didn't think were possible in nature. And let me just dive into three fundamental principles of quantum mechanics based on which a lot of the theory is developed. One principle is that quantum mechanics is irreducibly probabilistic. So in the quantum world, in the atomic scales, we always deal with probabilities, and we can never get rid of them. It's not probabilities like the stock market or the weather forecast, which is uncertainty because of lack of information. It's just too complex, so we don't know how to explain everything that affects it. No, in quantum theory, the probabilities are fundamental. We can never get rid of them, and there's no way to explain where exactly they come from. So that's a very unusual feature. Another very striking feature is so-called notion of superposition. And this is different forms of existence of states that particles can have, which we do not usually observe in everyday life. So colloquially, people say that particles can, for example, exist at the same time in different positions. They can be in different places at the same time. But these are words that we use to explain a phenomena that we just simply don't have a good intuition for. And then finally, quantum particles also exhibit correlations that we cannot explain otherwise without this new theory. And these correlations really can correlate at arbitrary distances these random events that occur in the quantum realm. So even though these events are random, they can be perfectly correlated at arbitrary distances with other random events. And this is something that is not possible to explain or even describe without the laws of quantum mechanics. So these three fundamental principles are not the only ones that explain quantum mechanics, but they're some of the fundamental pillars. And they're very different from our everyday intuition, but they're also very different from how we explain gravity. And so on the quantum realm, we understand them now so well that we start to exploit these unusual phenomena. So we understand them both in theory, what they mean, where they come from, and also how we can actually make use of them. And so this is the development of quantum technology, which is taking place in the last few years and is continuing at a rapid pace. How do we exploit these phenomena for applications? Now, in this talk, in the next few minutes or so, I also want to motivate that there is even a new fundamental type of research questions that we ask for them, which go beyond applications. Namely, can we leverage some of these unusual properties of quantum systems in order to learn something about gravity in the quantum realm? And the answer to that is yes, we can. And there's a lot of exciting opportunities for us to explore how these two theories merge at some scale. Now, when we have these two theories, at some point they meet. So gravity is very different. It bends space and time and predicts black holes, and quantum mechanics describes atoms. But we do not assume that any of these theories have actually a limit. It's not baked into the theories. Maybe they do, but that would be a new discovery. So at some scale, they should merge such that both of these principles somehow combine into some new effects. And where we expect these new effects is at very, very extreme conditions. And these conditions are captured by what we call Planck Scale. The Planck Scale is really just a kind of an estimate of where these effects become inevitable. But maybe we can see them even in other scales. But they become inevitable, for example, at spatial distances, which are 10 to the minus 35 meters. So this is extremely small. And again, for us, not just unimaginable, but also there's no experiment that can possibly go down to these scales. Or equivalently, we can define an energy scale at which these effects would take place. And this energy scale is so gigantic, it's about 15 orders of magnitude larger than what we can achieve in the LHC at CERN. So there is no hope that we can directly probe these scales, at least not with current technology. So is there even anything we can do? Because this is a big outstanding challenge in physics, how we can combine these two theories. Not only is it a mathematical challenge, but it's also an experimental challenge, because there will be new phenomena hiding there somewhere, new effects that we just don't know anything about them, but how can we reveal them? And so in my work and in our group, what we study is how we can leverage some of these new quantum technologies to answer some of these questions. Not to solve the full problem of quantum gravity, which is the so-called theory of everything, where there's a lot of efforts going into it, but because it's still an outstanding challenge, rather to show how experiments can help guide some of this process. Now, quantum technologies are really the control and the usage of these quantum effects that I mentioned. So for example, we can have quantum communication, which is just using this probabilistic nature of quantum theory in order to create fundamentally secure cryptography. So this is one application. Another application is quantum computing. And what it does is it leverages these correlations that I mentioned and also the superposition principle, which only exists in quantum mechanics, in order to create a process which can exponentially faster compute certain problems. So this is at the basis of quantum computing. And then finally, we also have quantum sensing, which is the ability to sense something better by leveraging, again, quantum correlations and superpositions for enhanced precision. So all of these applications have in common that we take some of the fundamental principles that only exist in quantum mechanics and try to find ways how we can leverage and utilize them. Now, the same we can do to try to understand the notion of gravity better in the quantum realm. And the reason for that is because we have many different new systems that become available in the laboratory. So on the one hand, just to give you two examples, on the one hand, we have atomic clocks. Atomic clocks are just clocks which are using atoms as a fundamental measure of time and atomic transitions. And what you can see here in this plot is that the precision at which we can measure time has grown not only exponentially in the last decades, but even doubly exponentially, where the exponential itself is increasing in the past few years. So this is an extreme advancement in technology, which allows us to probe timescales which were just unthinkable even just a few years ago. And another development in quantum technologies is the so-called framework of quantum optomechanics. And that is we interface larger systems by controlling interactions of it with light or microwave systems. Because we can control light and microwaves so well in the quantum realm, we can also use them as auxiliary system in order to control ever larger objects. And so this optomechanics spans mass ranges of systems from nanograms even all the way up to kilograms in different architectures, where we can probe, test, and control quantum phenomena at these mass scales. So this really pushes the limit of quantum mechanics into everyday macroscopic scales. And that opens the route to really study new phenomena in relation to gravity. So on the one hand, we can use these systems that we can control to simulate effects that we expect in gravity, or to find analog systems, such as analogs of black holes in systems that exhibit quantum phenomena. We can also use them, such as these atomic clocks, because they become so precise using quantum phenomena in order to measure some of these extremely minute effects, which we otherwise wouldn't have expected to be measurable, such as gravitational waves. So even though they don't use quantum effects yet, using quantum phenomena and quantum precision allows you to push it further such that we can improve our sensitivity. So these are some of the straightforward effects. We can also apply some of these concepts of quantum phenomena to the all of cosmology and all of the universe to see what kind of predictions it might give. Then some of the concepts that we have encountered in quantum technologies, we apply also to our fundamental understanding of gravity in order to try and see how these phenomena merge, such as using entanglement in the context of space-time geometry. But the two main topics that my group is interested in is to study, on the one hand, quantum gravity phenomenology. And that is to look for effects which potentially stem from a theory of quantum gravity, but which affect these kind of quantum systems that we have in the laboratory. How well can we actually test some of the possible predictions of quantum gravity? And the second possibility that we can study is to look at how these quantum technologies actually change in their behavior if they're experiencing some of these unusual effects of gravity, such as the change flow of time. So like I mentioned, for example, gravity bends time, and that in turn will affect how quantum technologies act if they feel this curvature of time. And so we study these effects, and it turns out there's new effects appear that will soon be visible in experiments. And so now in the last, I think, a few minutes that I still have, I want to just zoom in to give you just one flare and an example of how we can use these kind of novel systems in order to probe some specific models of quantum gravity. We don't have a full theory of quantum gravity, but we have some models that predict some changes in the quantum behavior of systems. And one such example of models is that it is widely expected that at some scale, quantum gravity will change the so-called Heisenberg uncertainty principle. Now, many of you, I mean, even if you're not physicists, are probably heard of the Heisenberg uncertainty principle. And what it tells us is a fundamental principle of quantum mechanics. It tells us that we cannot simultaneously measure both the position and the velocity of a particle or momentum of a particle. So both of these things cannot be known simultaneously to arbitrary precision. However, in quantum mechanics, it's possible to measure only one of them to arbitrary precision if you don't care about the other. And these models of quantum gravity change that as well. So what we widely expect is that there is even individual measurements, even of just position or velocity, are restricted in this kind of new theories at some scale. And so just to give you here a graphical representation of that, what you see here, this red curve, is just a representation, if this was an equal sign, of how well we could know both the position and the momentum. So if you have some uncertainty of position, we will also have some uncertainty in momentum according to normal quantum mechanics. But according to this modified theory of quantum gravity, and there's an additional factor here, which changes the behavior. And so at scales where we usually perform experiments, they're nearly indistinguishable, these two curves. But at small scales, there is a very fundamental difference, which is this appearance of this fundamental minimal length. So there's a gap here between the origin and where this blue curve bends. And this minimal gap has to do with the so-called Planck scale that I mentioned previously. So what these models do is they tell us that there's a minimal measurable notion of space, which is just the Planck length times some free parameter. And now this free parameter we call beta naught. It just basically parameterizes us where gravity and quantum mechanics meet. And so from just a few years ago, this parameter was very little bounded. The bound we had from experiments, from observations, were that this parameter is just smaller than 10 to the 33. And if it was really some new effect at the Planck scale, we would expect this parameter to be of order 1. So just to say that the Planck scale is very far away from observations. But it turns out we can leverage quantum control to do much, much better in order to test these type of models. And just in 2 slides to give you a flair for it, the fundamental principle that we use is a same principle that is being used in quantum computing as well. And in particular is the following. If we have a specific quantum system or a quantum state, we can change the position of the system, and we can also change the velocity of the system without measuring it. And this is what we call a so-called displacement of the system. So we can displace the position and the momentum of a system by a certain strength. Now the special thing comes if you try to displace the system twice. If you do 2 times a change of position and momentum, not only do we overall change both position and momentum, but we also imprint an overall phase shift on the system. And that is a uniquely quantum phenomenon, which is inherently linked to the Heisenberg uncertainty principle. And there is a certain operation we can do, namely we can move a system around a loop in phase space, meaning that we change the position and the momentum of the system in such a way that after the operation is done, the system just comes back to where it was originally. And so normally nothing would have happened to the system. But in quantum mechanics, there is an overall phase shift that is imprinted, which has to do with this uncertainty principle. And this phase shift, like I said, is leveraged. It has been realized about 20 years ago, and it has been leveraged for many years already in experiments with ions in order to implement some of the operations that we need for quantum computing. Now, what we showed in our research is that we can do the same with this very massive optomechanical systems that I mentioned, where you have lasers that interface a small mirror and displace the mirror through radiation pressure. So because photons have momentum, they can displace a mirror. And if we have many photons and strong enough interactions, they can imprint quantum effects onto this mirror. Now, we can use exactly this previously mentioned displacement scheme in order to test for how the uncertainty principle manifests itself on this massive mechanical mirror and oscillator. And in particular, what we proposed was to use a specific laser pulse, which is very short, but interacts with a mirror inside a cavity in such a way that the interaction is very strong. And it's strong because these cavities have a very large finesse, meaning that the photons that are inside the cavity bounce many, many times. And now we propose a specific scheme where you interact with the laser pulse and this mirror 4 times at different instances of time. And this is in order to implement this type of displacement that I showed previously in a specific way. And this operation we can characterize mathematically through these 4 different exponential factors. Now you can see they're all basically the same. It's only changing in position and momentum here of this blue system, which is the mechanical mirror. But the crucial part is that we have to swap these 2 exponential functions in order to cancel what is here on the other side. So you see that this minus p cancels plus p, minus x cancels plus x, but we need to swap them. And when we swap these operations, this is precisely how the Heisenberg uncertainty principle comes in. Now it turns out in quantum mechanics, this imprints a certain phase shift on the optical pulse. And this is related to what I mentioned in the previous slide. But if we have modifications of the uncertainty principle, no matter what they are and how minute they will also show on the phase shift on this optical pulse. And not only do they show on the optical system, they're also potentially enhanced non-linearly depending on how you perform this interaction. So you gain through such a system twice. One is you don't actually measure directly the uncertainty principle, you measure an effect of it on the ancillary system, which you can measure much better. And the second effect is that you have a nonlinear enhancement.
Igor, I'm very sorry, I'm afraid that you'll have to stop here.
That's perfect, because that's exactly the end of the slide.
Okay.
And so, so this is the very end of it. And the punchline is just simply that with such a system and leveraging quantum control, we can get to a regime where we can measure these type of models of quantum gravity at a scale which correspond to the Planck scale. And there's many experiments now ongoing, pushing this limit of this pre-parameter further closer to 1. Now with that, I just want to finally only show a slide of the interest of my group. On the one hand, we study quantum information processing and how we can use it for application. And the other hand, we also study the same effects for how we can use it to study gravity and even how gravity interfaces with quantum physics. So with that, thank you for your attention. Please, if there's any question, let me know.
So I may ask a quick question.
Of course.
Yeah, Igor, so what, it's of general character. So what kind of analog systems you are envisioning for the cosmology, like for black holes?
So there are studies of analog systems for black holes, which could have different forms. It depends on what specific property of the black hole you want to study. So basically, many analog systems that have any intrinsic speed at which information is propagating also can potentially have intrinsic horizons. And so horizons are those horizons that give rise to the black hole not being able to kind of emit from whatever is inside of it. And something similar can happen in other systems where they have a speed of propagation which is finite, just not the speed of light, but a different speed. And so there's examples such as metamaterials, where you have the propagation of light inside of metamaterials, which is much slower than usual propagation of light. And you can shape how the light is propagating inside in order to mimic how a black hole would act in the vicinity. So that's one example of such a system. Other systems are also actually, there's hydrodynamical systems, which also exhibit similar properties, but where you cannot study quantum effects.
I see.
Well, since I was over time anyway, I guess that counts for a shorter question session. But if there's any interest or questions, please anytime feel free to shoot me an email.